Washington State University. Go Cougs!
Okay. So now let's look at some performance, and so we will basically do start to finish, which is what we did, and we have this construct, right, which we already saw. We used OpenMP get W time. If you're using MPI code, you will be doing the wall clock time supported by the MPI function. And then you want to say what is the elapsed time between this step to that step, right? So you the time here, time there, take the difference. Okay. So let me introduce you to some basic concepts. You have been talking about speedups, but what is the expression for that? How would you calculate speedup? Okay. So first, before we define speedup, we want to understand what is a runtime in the serial context and parallel context. Okay. So we will use P as the number of threads that we are using. The serial runtime is whatever your serial code takes. That's your serial runtime. Meaning, if you use one thread, okay, that's how much time there is for the serial runtime. Parallel runtime is when you have P threads, what is the total time that has elapsed. Okay. So parallel time is essentially, each thread is taking whatever amount of time. So parallel runtime will be equal to the maximum time, maximum time for the longest running thread. Correct? In other words, since you have a process, once you have a main function, that's your main process, which is also your master thread. If you are clocking the entire code, right, the time to basically finish executing is your parallel runtime, the time for the master thread to finish. But if you are timing individual portions of your code like we did here, then the longest running thread, which may or may not be the master thread, will define what the parallel runtime for that section of code. Okay, make sense? Now, which also means when you have a longest running thread in a particular parallel region, the other threads might have finished early, but they sit and wait. They are idle, right? And we don't want them to be idle. So the parallel time equals serial time divided by P, which is wrong. Actually, we should change the slide. No, it's not right. Because parallel time is what you observe. Ideally, we would like it to be that. Right? So that's that it should be that. But it's not. Yeah. Okay. We should fix that. So let's ignore this. But speedup equals how much time your serial code took divided by how much time your parallel code took. Remember, this number is going to be greater than or equal to, or hopefully greater than or equal to this number. Right? So your speedup should grow as you keep increasing the number of threads. So typically you plot speedups like this. I think I have some charts and I'll tell you, something. So there are two ways to study scalability. Scalability means does my code scale with the number of physical cores that I keep using, number of threads I use. Okay. So there is a notion of strong scalability and weak scalability. I'll explain to you in this example. So let's say we record our time like this in the form of a simple table. So here is along the rows, I change the number of the input size. I grow the input n, right? 1,000 elements, 2,000 elements, whatever, 4,000 elements. And as as computer scientists, we are actually trained to just either keep doubling or keep offing, work in powers of 2, in other words. The reason is actually there is a nice mapping to the log function. Okay, that's why. But it's a general practice to essentially double your input size and double the number of processors or threads that you want to use to study scalability. Okay, it has its advantages. Okay, so that's why I've doubled the n and doubled the p here. Now let's say we ran some code, arbitrary code, doesn't matter what it is, but we observed some runtime. So each cell here says, okay, for this input size, for that number of threads, how much time it took. Okay. Now using this simple table, we can study scalability in two different ways. One way is to say, fix the input size, meaning fix the input here, and see how my code improves in runtime as you keep increasing the number of threads. This way of studying is what is called strong scaling behavior. This is harder to achieve as the number of threads keep going up. The reason is what we just discussed. Basically, you are keeping the input size fixed. If you keep the input size fixed, you are keeping the input work also fixed. If you keep the input work fixed and you keep increasing the number of resources available, at some point the resources don't have sufficient work to do. So they are sitting and wasting resources, and basically they're talking to one another, overhead starts to come in play. Okay? So which leads to the second type of analysis, which is called weak scaling. Don't look at a row, but look at the diagonal in this table. Here what you do is, when I grow the input, let's say double, I also grow the number of processors by the same factor. So in other words, if I have double the amount of work, I double the number of cores so that my time roughly remains fixed. Let's say I want to meet a time budget. I don't want to exceed 10 minutes of execution. And if I achieve that 10 minutes of execution using 100 cores for some input size, and if I have a new input which is double that size, I will deploy double the number of cores, 200 processors, so that the time is expected to be fixed. Okay? This notion is weak scaling. So what a good well-written code typically has roughly the same values along each of these diagonals. Okay? It's called weak scaling because what you're saying is, you're doing a little bit of cheating. You're saying, I'm going to increase the system size, but I'm also going to feed it more work to do, which actually is what we do in practice. Why bother asking more resources if you have already solved the problem in a smaller number of processors? Your goal for using larger number of processors should be to solve a larger problem, right? That's the notion of weak scaling. So we can study all these types of speed ups, and there are actually multiple different types of speed up. So from the table that I just showed, you would want to represent your results like this and convince yourself that this code scales. So on the left hand side is simply a runtime as a function of number of processors or number of threads. On the right hand side is the speed up as a function of number of threads that you used. Okay, all I did was took this table and converted it into these two charts in Excel, right? So said, okay, let's look at the speed up. It says, or let's look at the runtime first. If you double the number of threads, and each arc here or each line corresponds to a given input, if you double the number of threads, your runtime should half, right? In the speed up world, if you double the number of threads, your speed up should double, right? So I should get roughly a speed up of 2 on 2 threads and 4 on 4 threads, right? So this orange or yellow or whatever the color is, that line is the ideal curve. It's what you would expect, you should expect in an ideal world. Then the more you deviate from that, the less speed up you get. And if you notice, for this code, this blue line has deviated a lot from the ideal. It's not getting the best possible speed up by a large margin. And then we look to ask the question, why did it not get the speed up? Well, that's because the input size is the smallest there. The work was not sufficient to keep the system busy. Make sense? So typically this is what you would see in standard codes. The smallest input size, the speed up tends to taper out sooner than for the larger input sizes. Okay? So there is this notion of Amdahl's law, which basically says, in the strong scaling, meaning if you keep the input size fixed and keep increasing the number of threads, at some point you will hit a plateau in the speed up. Your speed up won't keep increasing all the time. You will reach a limit. Beyond that point, if you add more threads, it's of no use. In fact, the speed up may go down. Okay, that's Amdahl's law. It's a limit on how much speed up you can achieve. Then came along another person called Gustafson, John Gustafson, who proposed something called the Gustafson's law, which says, no, don't keep the input size fixed. That's the wrong way to use parallel systems. Increase the work as you increase the number of cores. You'll basically see the time flatten. That's weak scaling. That's called Gustafson's law and so on. Okay. All right.
So that what's the speed
Speed up.
is that just a result
Great question, yeah. So speedup is, why we are not getting the ideal speedup is primarily because of the overhead that's associated in managing a parallel system. After all, the master thread in this context in OpenMP, right? Master thread has to spawn p minus 1 threads because it is one of the p threads, which means it has to do some work to spawn off those p minus 1 threads. It needs to do some housekeeping. Who is who? What is the space for that? Who is shared variable? What should I expose to these individual threads? That's all overhead, housekeeping. Then it needs to watch who is finishing at what rate, and then it has to detect all the threads are finished, I'm done with my parallel region. All this is overhead, additional, which is not there in your serial code. It's because you have a parallel code, you're doing additional work, right? That's the overhead. So typically, the parallel time equals this. It's better to talk in terms of work actually. This parallel work is equal to the serial work times the number of p, number of processes used, plus the overhead, the additional time that you took, that your serial code did not take. Make sense? So there is a notion of efficiency which I don't want to go into now. After speedup, we should be talking of efficiency. An efficient system is one where the overheads are minimal. Okay? That's what we should aim for or strive for. Speedup sometimes can be very deceiving. I can inflate my serial computation time to show you very good speedup results. That may not mean much, right? I mean, I can add dummy calculations or computations in my code just to make my reference, which is my serial computation time, a lot, and then I'll show you nice speedup results, right?
So is your scope of your shared variables, is that confined to like the variables defined within a function? I mean, how far does it go out to say I need to?
So whatever your programming syntax is, so if it is a variable that is visible only within a function, it will continue to stay only within the function, except internally to that function, if you spawn multiple threads, you are saying at that resolution, how would the threads see it? And then you're saying shared means the same copy is visible to all the threads within that function, or private, which means no, each thread will have its own copy.
But I'm just wondering if every variable is shared by default.
It's shared by default, yeah.
How far does it look out to see the variables? Or
So
like if you say I'm going to do an OpenMP, the next thing is a function, does it look at the function and figure out what all the variables are that need to be set up with the shared?
So if you have written a function and if you have initialized a variable before you call that function, and if that function, if that variable scope is not global, then that function internally will never see it, because the function will have its own set of variables, right? If you define the outside variable as a global, then the function will also see it. So this is to do with the standard C programming syntax as opposed to OpenMP. OpenMP does not alter that behavior. It only says for the variables I see now, whichever I'm in a section of code, I see a bunch of variables. Of those variables, how the individual threads should see. That's all the OpenMP runtime system decides. It doesn't determine which variable should be visible with function. That's to do with the C programming syntax or the Fortran programming syntax. Okay? All right. So we already did this, I think. We tried the loop.c just now. We ran, we got some speed up. So some useful exercise for you to do would be to record runtimes like this, put it in a chart, generate speed up curves, and see whether they make sense, right?